Hey guys, so lesson 3.2 should be a pretty short one. Just looking at some growth and decay models. Notice the layout of the formulas that we're working with on this really are the same as what we did in 3.1. It still fits the model of something times something to the x power, right? So our leading coefficient we're seeing as this p sub 0, or you could say like the initial amount is usually a good way to look at this. We have our rate, so there's some percent involved, and then we have t usually represents time with these guys. So if you have a base greater than 1, just like we talked about in the last section, then we know it's going to be a growth model. If your base is less than 1, we know it's going to be a decay model. So if the rate that I am applying is supposed to represent growth, right? If we said like we're investing money and our money is earning more and more at a certain percent, then we do 1 plus the rate in order to create the base. If we are losing money, then it's going to be represented by doing 1 minus the rate in order to get whatever this new base is going to be. So the R that you see is either a growth rate or a decay rate, or a growth factor or decay factor, just depending on the description of what's taking place. If we talk about, like I said, investing money, that mean and my money is increasing, then I would need to do 1 plus that rate of whatever it is. But if we're losing money over time, like let's just say it's like a new car, it's going to lose money over time, then this percentage rate is going to be our new value is going to be going down, and so we're going to do 1 minus the rate in order to get our new base. So as you look at these first couple, they just wanted us to be able to identify, first of all, is it growth or decay, and what's the rate? What's the growth rate or decay rate? So as I look at these, clearly on the first one, it's a value bigger than 1. So it must be growth. So I know whatever is in parentheses must represent 1 plus the rate because it's growth. So you can see in order to figure out the rate, all I really have to do from that is subtract 1 from both sides. So the 0.034 is going to represent our growth rate. We could keep that as a decimal, or you could write that as 3.4% is going to be our growth rate. On this one, you can see that it's a value less than 1, so I know it's decay. So I know whatever number is in parentheses must represent 1 minus the rate. So on this one, if I'm getting R by itself, eventually what you're going to be doing is basically doing 1 minus whatever this is in order to get R by itself, right? So if I did 1 minus the 0.923, I'm going to get points, I believe it is 0.077, or you could say 7.7% would be my decay rate. So in short, the simple way of looking at that is from this I can do subtract 1 from this, and this I can subtract from 1 if it's decay. So that's going to be the basic process. So here's just a basic word problem. If you went out and bought yourself a nice new $25,000 car, well, of course, as soon as you drive it off the lot, it is going to start decreasing in value. The first year it loses the most. The second year it loses not quite as much as the first year, but it kind of keeps going in this decreasing rate. So if we wanted to just represent this in a model, because it is depreciating, or because it is losing value, I know I need to do it in the decay model where I do 1 minus the rate. So I have the initial value. This is what you started with. We're going to do 1 minus the rate to whatever years, right? So this is just the general model for any amount of time. So if I wanted to know how much is it going to be worth after the first year, I would just plug in a 1 for t. If I want to know how much it's going to be worth after 2 years, I plug in a 2 for t. This one in particular is saying how much is it going to be worth after 5 years. So if I were to plug in a 5 for t, and that's usually the amount of time it takes to pay off your car. Typically it's a 5-year loan, so I'm just cleaning up the inside of those parentheses a little bit. And we're going to do this for 5 years. So here's what we're going to put into the calculator. So if you really paid it off in 5 years, which is pretty normal for a car, how much? Let's just say you wanted to resell it. What's it worth after you're done paying it off? So that $25,000 car is now worth $11,092 by the time you have it paid off. So if you were going to, say, sell it at that point, this is about what it would be worth 5 years later. All right, let me keep it moving for you. So, and again, this whole section is about taking those growth and decay models and just applying them to these like word problem type scenarios. So for this one, we have 200 bacteria. In other words, that's the initial amount. That's what we're starting with. Put into a petri dish, and it doubles every hour. So what they want to know is how long will it take for it to become 250,000. Notice we're starting with 200. It's going to double every hour. And they want to know how many hours is it going to take till we have 250,000, right? So they're laying out sort of a model for you so that you can see where this setup comes from. But essentially, the 200 is what we started with. That's our leading coefficient, or P sub 0, the initial amount. And then the base that we're using is our growth rate. So if it's going to double every hour, then our base is 2. Because it's doubling every hour, and they show you why within a couple examples right here as to why that works with that base of 2. So T represents our time. Eventually, we will be solving this using logarithms, but because that comes up a little later in this chapter, what they want us to do first is try solving this on a calculator. So real simple, and we've done ones like this already this year. So what we're going to do is go in and graph our 200 times t to the x, times 2 to the x. And our future amount is going to be that 250,000. And so what we're saying is, when are those two things going to meet, right? When is our function going to equal 250,000? Clearly that's a giant window. I'm going to have to increase my y values quite a bit here. So let me, I don't know exactly what this will look like yet, but we're going to find out together. So I'm going to go all the way up to 300,000 just to make sure I get it on my screen. Let's just see if I covered it, if it's going to take less than 20 hours here. So here's our growth function, and then here comes the 250,000. And again, what we want to know is, where do those two things intersect? Where are they equal? When does my function equal 250,000? So if we go under Calc and choose Intersect, hit Enter, it's going to ask you some questions. You just kind of keep hitting Enter. So when it says first curve, just hit Enter. Second curve, just hit Enter. And then guess, hit Enter one more time. And we can see that it's going to take about 10.3 hours in order for us to come up with 250,000. And so for now, that's how we're going to solve them. Like I said, we're going to be doing that with logarithms in the near future. But that's what we can do for this lesson. And let me take you to this last page. And let's do a decay problem. So on that last one, notice our substance was doubling, so our base was 2. But another kind of common type of problem is something called a half-life, which means instead of doubling every hour or doubling every whatever, this one is being cut in half over certain periods of time. So now our base is going to be a half instead of 2. right? So that when they give you these kinds of descriptions, we're applying that to our base. So this one started with 10 grams, right? That was our initial amount. So notice that's our leading coefficient is the 10. Because it's a half-life and it's being cut in half every 24 days, the 1/2 is our base. The tricky one is the exponent, right? So we are looking at periods of time per 24 days. So notice that T represents time in days, right? So if only 1 day goes by, remember it takes a full 24 days to cut in half. If only 1 day goes by, then it's only going to be 1 out of the 24 days that we would be applying to this, right? And so it'd be a pretty small change. If you said, if T was 24, so 24 out of 24 days now represents 1 full period of time that it would be cutting in half, right? So the easy way to say that is it's always going to be T over whatever it takes for the substance to cut in half. So if it were to take, say, 7 hours to cut in half, or if the half-life was 7 hours, then we would say T over 7, and T would represent hours. And so we just have to apply it to whatever they're giving us right here. So what they were asking in this problem was, okay, you started with 10 grams. How long is it going to take for that 10 grams to become 2 grams? And so we could just do the exact same approach. We are just setting our function equal to 2. I'm just going to write it out here. So we started with 10. It's a half-life. And we're looking at T over 24. And again, we'll be solving these down the road with logs, but for now, we're just going to be finding the intersection of these two graphs. So, and you can get an idea of the window I'm going to use right down here, right? It's got to be at least 60, if not higher, so that we can see the intersection on this. And sometimes you just have to play with those numbers until you find a winning combo. So I have my 10 times 1/2 to the x over 24. And we want to know when is it going to become 2. So let me go back to this window here. Definitely doesn't need to be this high. So let's see how that looks. So there comes our decay graph. And here comes the y equals 2. And all I'm looking for is where those two guys intersect. So go to calc, go to intersect, hit enter, enter, enter. And so at about 55.7 days is when my 10 grams becomes 2 grams. So those are your half-life problems. And that is it for this section.